What if I told you the universe is expanding so fast that some galaxies are racing away from us faster than the speed of light? It sounds impossible, like something out of a science fiction movie, but it's real. Right now, the fabric of space itself is stretching, carrying entire galaxies along with it, and the farther they are, the quicker they vanish into the cosmic horizon. This isn't just a curious fact, it's a glimpse into one of the deepest mysteries of our existence. How can anything move faster than light? What's driving this relentless expansion? And perhaps the most haunting question of all, where is it all heading? For all our advancements in science, the universe still holds secrets that defy even the sharpest minds. Dark energy, the mysterious force accelerating this expansion, remains utterly invisible, undetectable by any instrument we've built. We can see its effects: galaxies flying apart, space itself growing colder and emptier, but we have no idea what it actually is. And that's just the beginning. There are at least 25 unsolved questions about the universe's expansion that keep cosmologists up at night. Some challenge the very laws of physics as we know them. Others hint at realities beyond our comprehension, parallel dimensions, hidden forces, or even flaws in Einstein's theory of relativity. But here's the beautiful part: every unanswered question is an invitation. An invitation to explore, to wonder, to stand at the edge of what we know and peer into the unknown. In this video, we're going to journey through those 25 cosmic mysteries together, from the enigma of dark energy to the fate of the universe itself. Whether it ends in a fiery collapse, a frozen silence, or something even stranger, one thing's certain: the story of our universe is far from over, so let's dive in. The cosmos is waiting. Picture a force so powerful it's ripping the universe apart, yet so invisible we can't even detect it directly. That's dark energy, the phantom engine behind the universe's runaway expansion. Back in the late 1990s, astronomers made a discovery that turned cosmology upside down. They were studying distant supernovae, those brilliant stellar explosions used as cosmic mile markers, expecting to find the universe's expansion slowing down due to gravity's pull. Instead, they found the opposite. The universe wasn't just expanding, it was accelerating, as if some invisible hand was pushing everything apart faster and faster. Here's what makes dark energy so baffling. It's not just unknown, it's unlike anything else in physics. We estimate it makes up roughly 68% of the universe's total energy, dwarfing everything else from galaxies to dark matter. Yet we've never seen it, measured it directly, or even fully understood how it works. The leading explanation is Einstein's cosmological constant, a kind of energy woven into the fabric of space itself, driving expansion at a steady rate. But there's a problem. When we calculate how strong this energy should be using quantum physics, we get a number trillions of times larger than what we observe. That mismatch is so colossal, it's like predicting a gentle breeze and getting a hurricane instead. Another theory suggests dark energy isn't constant at all. It might be a dynamic force called quintessence, ebbing and flowing over time. Some models even propose that dark energy could eventually tear apart galaxies, stars, and even atoms in a catastrophic big rip. But here's the catch: every experiment so far has come up empty. We're left with more questions than answers. Is dark energy a property of space itself, or something entirely new? Could it change in the future, or is it locked in place? And most chillingly, what if it's not the only force out there, just the only one we've glimpsed so far? One thing's certain: until we solve this puzzle, the ultimate fate of the universe hangs in the balance. Imagine throwing a ball into the air, expecting it to slow down and fall back to Earth, but instead, it shoots upward faster and faster, defying gravity entirely. That's essentially what astronomers witnessed in 1998 when they discovered the universe's expansion wasn't just continuing, it was accelerating. This revelation was so groundbreaking it earned the researchers the Nobel Prize in Physics in 2011, and yet, decades later, we're still scrambling to explain how it's even possible. The discovery came from two independent teams studying distant Type Ia supernova, the cosmic equivalent of standardized light bulbs. These stellar explosions always shine with the same brightness, allowing scientists to calculate their distance with precision. By measuring how much their light stretched or redshifted as the universe expanded, researchers could trace how the expansion rate changed over time. Everyone expected to find gravity gradually putting the brakes on the universe, like a car coasting to a stop. Instead, the data showed the opposite. The universe's expansion pedal was slamming down harder over billions of years, as if some unseen force were overriding gravity's pull. This threw a wrench into everything we thought we knew. Einstein's general relativity, our gold standard for understanding gravity, predicted that matter and energy should slow expansion, not speed it up. Some scientists initially questioned the findings. Could dust be dimming the supernova, skewing the measurements? Could there be unknown quirks in how these stars explode? But over the next 20 years, multiple lines of evidence from the cosmic microwave background to the large-scale structure of galaxies all confirmed the same unsettling truth. The universe isn't just expanding, it's in a hurry. The implications are staggering. If this acceleration continues, distant galaxies will eventually vanish from view entirely, their light stretched beyond detectability. Future civilizations might gaze into a night sky nearly empty of galaxies, with no clues that a vast cosmic tapestry once surrounded them. But here's the real puzzle: what's causing this acceleration? Dark energy is the leading suspect, but is it a constant force woven into space itself, or something more dynamic? Could it be a sign that gravity behaves differently on cosmic scales, or even that our universe is colliding with another in a hidden dimension? Each possibility raises more questions than answers, leaving us with a humbling reminder: the universe still has mysteries that defy our best theories. The Hubble Constant, the number that tells us how fast the universe is expanding, might sound like a fixed rule of nature, a cosmic speed limit etched into the fabric of reality. But what if it's not constant at all? What if it's changing, or worse, what if we've been measuring it wrong this whole time? This isn't just academic nitpicking. The so-called Hubble tension has become one of the most urgent puzzles in modern cosmology, with two of our most trusted measurement methods giving wildly different answers. Take supernova, for example. When we observe these exploding stars in distant galaxies, their light reveals how much the universe has stretched since they detonated. By comparing their apparent brightness to their known intrinsic brightness, we can calculate how far away they are and how fast space has expanded over time. This method gives us a Hubble constant value around 73 kilometers per second per megaparsec. That means for every 3.26 million light-years farther out we look, galaxies appear to be racing away 73 kilometers per second faster. But then there's the cosmic microwave background, the afterglow of the Big Bang itself. By studying subtle temperature fluctuations in this ancient light, scientists can extrapolate how the universe expanded in its infancy and predict what the Hubble constant should be today. The problem: those predictions land closer to 67, a full 6 points lower than the supernova measurements. At first glance, that might not sound like much, but in the precise world of cosmology, it's a glaring discrepancy. These numbers should agree. The fact that they don't suggest something fundamental is missing from our understanding. One possibility is that dark energy isn't the static force we've assumed. Maybe it's growing stronger or weaker over time, subtly altering the expansion rate in ways we haven't accounted for. Or perhaps there's an undiscovered particle, a shadowy cousin to the neutrino, interacting with gravity in ways that throw off our measurements. Some theorists even speculate that we're seeing the fingerprints of another universe brushing against ours, warping local spacetime in undetectable ways. The wildest ideas don't stop there. Could gravity itself behave differently on cosmic scales, breaking Einstein's rules just enough to explain the mismatch? Every attempt to resolve the tension so far has only deepened the mystery, calibrating instruments more precisely. Both methods keep yielding the same conflicting results. Accounting for unseen dust or measurement errors, the gap persists. This isn't just about refining numbers, it's a potential crack in the foundation of modern physics. If the Hubble constant isn't so constant after all, it means the universe is playing by rules we haven't decoded yet, and that changes everything. We can see galaxies billions of light years away, but here's the unsettling truth: we're actually trapped inside an invisible bubble. The observable universe, everything we can detect with our most powerful telescopes, stretches about 93 billion light years across. Yet that's just a tiny fraction of what's really out there. Beyond this cosmic horizon lies the unobservable universe, vast regions of space whose light hasn't had enough time to reach us since the Big Bang. And because the universe is expanding faster than light can travel across it, some of those distant realms will forever remain hidden from view. So what lies beyond the edge of our vision? One possibility is that space just continues, an endless sea of galaxies stretching into infinity, each one drifting farther into the darkness as expansion accelerates. But infinity isn't the only option. Some theories suggest our universe might be curved like the surface of a balloon. Travel far enough in one direction, and you'd eventually loop back to where you started. Others propose a dizzying idea called eternal inflation, where our entire observable universe is just one bubble in a foaming multiverse, with other bubbles constantly spawning new universes with different physical laws. Here's where it gets wild. If other bubble universes exist, they could be right next to us, separated by an impassable barrier of hyper-expanding space. Some might contain alternate versions of reality where gravity is stronger, time runs backward, or matter never formed at all. The craziest part, we may never know for sure. The unobservable universe could contain civilizations, structures, or even entire physics-defying realms that we'll never glimpse. This raises a haunting question. If most of reality is permanently hidden from us, how can we claim to understand the universe at all? Maybe we're like ants trying to map a continent by studying a single grain of sand. Yet even with these limitations, cosmologists keep pushing the boundaries. By studying subtle patterns in the cosmic microwave background or simulating the birth of multiverses, they're piecing together clues about what might lie in the ultimate blind spot. One thing's certain: whatever's out there, it's far stranger than anything we've imagined. Right now, the universe is stretching, gentle but relentless, like taffy pulled slowly apart. But what if that stretching turns violent? What if dark energy doesn't just push galaxies away, but grows stronger over time until it rips everything, stars, planets, even the fabric of spacetime itself, into oblivion? This isn't just speculation, it's a real possibility cosmologists call the Big Rip, and it's one of the most terrifying endgame scenarios for our universe. Here's how it would unfold. Today, dark energy's grip is subtle. It overwhelms gravity on cosmic scales, but here on Earth, we don't feel its pull. Yet if dark energy isn't constant, if it's a force that intensifies as space expands, then eventually, its power would become unstoppable. First, galaxy clusters would be torn apart, their gravitational bonds no match for the swelling force of expansion. Next, individual galaxies would unravel, stars spiraling into the void. Then, stars and planets themselves would fracture, their atoms ripped apart in a final, catastrophic instant. Even spacetime might shatter, leaving behind a chaotic sea of disconnected particles. The eerie part: we can't rule this out. Some models of dark energy, like phantom energy, predict exactly this runaway effect. And while the evidence isn't conclusive, there are hints. Measurements of distant supernova and galaxy distributions don't just show acceleration, they suggest the rate might be increasing ever so slightly. If that trend holds, the Big Rip moves from sci-fi nightmare to genuine scientific possibility. But it's not the only fate on the table. Contrast this with the Big Crunch, where gravity eventually reverses expansion, pulling everything back into a singularity, a mirror of the Big Bang. Or heat death, where expansion continues but slows to a crawl, leaving the universe a frigid, lifeless void. Right now, observations favor heat death, but the Big Rip lingers as a dark horse candidate, a reminder that dark energy could still surprise us. What makes the Big Rip so unsettling isn't just the violence, it's the timeline. If it happens, calculations suggest it could occur in as little as 22 billion years. On cosmic scales, that's the blink of an eye, and yet we might never know for sure until it's too late. The universe doesn't owe us answers, it simply unfolds according to rules we're still struggling to decode. So until we crack the mystery of dark energy's true nature, the Big Rip remains a silent specter lurking in the equations of our best theories. What if the universe's expansion isn't just happening in the three dimensions we know, length, width, and height? What if unseen extra dimensions, coiled up smaller than atoms or stretched across cosmic distances, are secretly tugging at the fabric of space-time? This isn't just wild speculation string theory. One of the most promising frameworks for unifying gravity and quantum mechanics predicts exactly that. According to this mind-bending idea, there could be as many as 10 or 11 dimensions, all hidden from our everyday perception, influencing everything from the behavior of particles to the fate of the cosmos. Take the concept of compactified dimensions. Imagine a garden hose stretched across a field. From far away, it looks like a simple one-dimensional line. But up close, you realize it's actually a cylinder with a tiny circular dimension curled around its surface. String theory suggests something similar might be happening with our universe. 6 or 7 extra dimensions could be curled up so tightly, perhaps 1 billion times smaller than an atom, that we'd never notice them directly. Yet their presence might subtly alter how gravity behaves over vast distances, potentially explaining why the universe's expansion is accelerating. Then there's the brain-world hypothesis, which takes things even further. In this scenario, our entire three-dimensional universe could be a brain, a kind of membrane floating in a higher dimensional space, like a slice of bread in an invisible loaf. Other brains might exist parallel to ours, separated by dimensions we can't access. Gravity, unlike other forces, might leak between these brains, weakening its pull over cosmic scales and making space appear to expand faster than expected. Some models even suggest that dark energy could be the gravitational echoes of collisions between our brain and others, ripples from unseen cosmic neighbors. The hunt for these hidden dimensions isn't just theoretical. Particle accelerators like the Large Hadron Collider are searching for microscopic black holes or unusual energy patterns that could betray extra dimensions. Meanwhile, precise measurements of gravity's strength at tiny distances, experiments so sensitive they can detect a feather's weight, are testing whether gravity behaves differently on scales smaller than a millimeter. So far, no smoking gun has been found, but the search is far from over. Here's what keeps physicists up at night. If extra dimensions exist, could they be the key to unlocking dark energy's secrets? Or might they rewrite our understanding of gravity entirely, revealing that Einstein's equations are just a shadow of a deeper, multidimensional reality? The universe has a way of hiding its most profound truths, but every experiment, every observation, brings us one step closer to peeling back the curtain. Einstein called it his greatest blunder, the cosmological constant, a fixed energy woven into empty space that could push or pull the universe apart. He abandoned the idea, but after the discovery of accelerating expansion, scientists revived it as the leading explanation for dark energy, an unchanging force that drives cosmic growth at a steady, relentless pace. But what if we've been wrong all along? What if dark energy isn't a constant, but a shape-shifting entity growing stronger or weaker over time? The answer could rewrite the ultimate fate of everything. Let's start with the simplest assumption, that dark energy is truly constant, as Einstein's cosmological constant suggests. In this view, every cubic centimeter of space, no matter how empty, hums with the same faint energy, stretching the universe like an unstoppable spring. The math is elegant. It neatly fits observations of distant supernova and cosmic background radiation. But there's a catch. When physicists calculate how much energy empty space should contain using quantum theory, the numbers are catastrophically off by a factor of 1 followed by 120 zeros. That's not just a rounding error, it's the biggest mismatch in science. Either we're missing something fundamental, or dark energy isn't what we think. Enter phantom energy, a nightmare version of dark energy that doesn't just push space apart, but grows stronger as the universe expands. Picture a car where pressing the accelerator also makes the pedal sink deeper, speeding you up faster and faster until the engine explodes. In cosmic terms, phantom energy could eventually overpower every force in nature, shredding atoms in a catastrophic big rip. Some models even suggest this could happen in as little as 22 billion years, a blink on cosmic scales. But proving whether dark energy changes is staggeringly hard. Unlike a chemical reaction we can replay in a lab, the universe gives us only one experiment, and we're stuck observing it from a single moment in time. Imagine trying to measure how a candle burns over centuries, but you only get to glance at it once. That's the challenge astronomers face. To track dark energy's behavior, they're stitching together snapshots of the universe at different ages: supernova from 5 billion years ago, galaxies from 10 billion, the cosmic microwave background from 13.8 billion. Each clue is a pixel in a blurry, incomplete picture. The latest twist: some data hints that dark energy might not be constant after all. Measurements of ancient galaxy clusters suggest the acceleration rate could have been slightly slower in the past. It's not yet conclusive, like hearing a faint whisper in a thunderstorm. But if true, it could mean dark energy is a dynamic field, like a fifth force of nature slowly awakening. Theorists have names for these ideas: quintessence, a kind of cosmic fluid thinning over time, or K-essence, which clumps and ebbs like a strange tide. Even wilder possibilities lurk in the shadows. Could dark energy be a sign of our universe colliding with another in a hidden dimension, or evidence that gravity itself behaves differently across cosmic distances? Every option forces us to confront how little we truly understand. The irony is delicious. The force driving the universe's expansion might be the very thing that keeps cosmologists up at night, stretching their minds to the limit. One thing's certain: if dark energy isn't constant, the implications are cosmic. It could mean the universe won't just fade into cold emptiness. It might tear itself apart, collapse, or even bounce into a new cycle of existence. For now, all we can do is keep watching, measuring, and wondering. The universe holds its secrets close. Think of the universe's birth like a balloon inflating, not the slow, steady expansion we see today, but an explosive growth spurt so violent it stretched space itself faster than light. This is cosmic inflation, a theory that solves some of the biggest mysteries about our universe but leaves us with an even bigger question: what set it off in the first place? For a fraction of a second after the Big Bang, somewhere around 10 to the power of -36 seconds, the universe didn't just expand. It hyper-expanded, doubling in size at least 80 times over in intervals shorter than the blink of an eye. This inflationary epoch smoothed out wrinkles in spacetime, explaining why the cosmos looks so uniform in every direction. It also planted the seeds for galaxies and galaxy clusters through minuscule quantum fluctuations stretched to cosmic scales. But here's the puzzle. What unleashed this primordial sprint? Leading theories point to a mysterious quantum field called the inflaton, a kind of energy syrup that permeated the early universe. As this field decayed from a high-energy state, it released energy that powered inflation's runaway expansion. Picture a marble rolling down a steep hill, gaining speed until it hits flat ground and slows. The inflaton field might have worked similarly, with its slope determining how fast and how long inflation lasted. But we've never detected this field directly, and its properties remain purely theoretical. Another idea suggests a cosmic phase transition, like water freezing into ice. The early universe could have shifted from a chaotic, high-energy state to a more stable one, releasing latent energy that drove inflation. Some models even propose a collision between higher-dimensional branes in string theory as the trigger, an event so violent it birthed our entire cosmos. The hunt for answers lies in gravitational waves, ripples in space-time left over from inflation's furious stretching. Experiments like BICEP and the upcoming Light Bird aim to detect these primordial waves imprinted on the cosmic microwave background. Finding them would be like uncovering fingerprints at a crime scene, offering clues about inflation's energy scale and duration. But so far, the signals have eluded us, either too faint to spot or masked by cosmic dust. What makes inflation so fascinating isn't just the physics, it's the sheer audacity of the idea. A process that lasted less than a second shaped everything we see today, from the largest galaxy clusters to the voids between them. Yet without direct evidence, inflation remains a brilliant hypothesis in search of confirmation. Was it a quantum fluke, a collision of unseen dimensions? Or something even stranger lurking beyond the edges of our current theories? Until we know, the inflationary epoch stands as one of cosmology's most tantalizing open cases. We picture the universe expanding like a perfectly rising loaf of bread, every raisin in the dough drifting apart at the same steady pace. But what if reality is messier? What if some regions stretch faster while others barely move, like lumps in uneven batter? This isn't just speculation. Mounting evidence suggests cosmic expansion might not be the smooth, uniform process we've assumed, and the implications could upend our understanding of dark energy itself. Take the mysterious bulk flows. These are colossal rivers of galaxies, thousands of them, all streaming in the same direction at speeds surpassing 600 kilometers per second, far faster than standard expansion models predict. It's as if some invisible current is tugging them off course. The most famous, the dark flow, extends billions of light-years toward a point beyond the observable universe's edge. Could this be the gravitational pull of a supermassive structure we can't see? Or is it a sign that dark energy's push isn't uniform, creating cosmic tides that warp motion on unimaginable scales? Then there's the problem of voids, those vast, almost empty regions between galaxy filaments. Some appear to be growing faster than expected, their edges stretching like overinflated bubbles. Meanwhile, dense galaxy clusters seem to resist expansion, as if dark energy's grip is weaker where matter huddles close. This patchiness challenges the idea that dark energy is perfectly smeared across space. Maybe it clumps or fluctuates, like fog, thinning in some areas and thickening in others. The stakes couldn't be higher. If expansion isn't uniform, our cosmic yardstick supernova, Baryon acoustic oscillations might need recalibrating. Distant galaxies could appear to accelerate not because dark energy is strengthening, but because we're misreading how space stretches locally. Worse, it might mean dark energy interacts with matter in ways we haven't accounted for, hinting at undiscovered physics. Some theorists propose radical solutions. Maybe dark energy is tied to quantum vacuum fluctuations that vary across the cosmos. Others suggest we're seeing echoes of an ancient collision with another universe, leaving scars in the expansion pattern. The wildest idea, that we're stuck in a low-density bubble, where our local expansion rate isn't representative of the universe at large, a cosmic version of living in a quiet neighborhood while the rest of the city burns. For now, the data remains tantalizingly ambiguous. Surveys like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies to hunt for these irregularities. But one thing's clear: if the universe's expansion is a symphony, it's far more discordant than we thought, and dark energy might not be the steady conductor we imagined. Empty space isn't really empty, at least not according to quantum physics. Even in a perfect vacuum, particles flicker in and out of existence like cosmic static, their fleeting lives governed by Heisenberg's uncertainty principle. This quantum foam should sizzle with energy, enough, theoretically, to warp spacetime itself. So why doesn't it inflate the universe like a balloon? The answer, or rather the stunning lack of one, forms the heart of the vacuum catastrophe, a mismatch so colossal it's been called the worst theoretical prediction in the history of science. Here's the problem: when physicists calculate how much energy the quantum vacuum should contain, the numbers are absurdly large, around 1 followed by 120 zeros times stronger than what we actually observe dark energy to be. To put that in perspective, it's like predicting a single light bulb would outshine the entire Milky Way, only to measure its glow and find it's barely enough to read by. This isn't a minor discrepancy. It's a screaming red flag that something fundamental is missing from our understanding of how quantum mechanics and gravity interact. One possible explanation lies in the awkward marriage, or rather divorce, between quantum field theory and general relativity. Quantum physics excels at describing the tiny, probabilistic world of particles, while Einstein's relativity governs the vast, smooth curvature of spacetime. But when we try to combine them to explain vacuum energy, the math explodes. It's as if two brilliant musicians are playing different symphonies simultaneously. The result isn't harmony, but noise. Some theorists suggest cancellations might occur, where positive and negative vacuum energies balance out to nearly zero. Yet even if that's true, why doesn't the balance perfect? Why is there just enough residual energy left over to drive cosmic acceleration, a number so precise it teeters on the edge of nothingness? Another unsettling possibility is that we're misreading the quantum vacuum entirely. Maybe virtual particles don't contribute to gravity the way real matter does, like shadows that can't push objects even though they seem solid. Or perhaps gravity filters vacuum energy, only responding to certain wavelengths. Some radical proposals even argue that dark energy isn't vacuum energy at all, but an entirely separate phenomenon wearing its disguise. The vacuum catastrophe isn't just an academic curiosity, it's a crisis at the core of modern physics. If we can't reconcile these titanic theories, we might be forever stuck with a fractured view of reality, where the rules of the quantum world and the cosmos refuse to speak the same language. And until we crack this puzzle, the true nature of dark energy and the fate of the universe will remain just out of reach. What if our universe's peculiar expansion rate isn't a cosmic accident, but a lottery ticket pulled from an infinite multiverse? Picture a cosmic casino where countless universes flicker in and out of existence, each with different laws of physics. Some might collapse instantly, others expand so fast no stars ever form. Ours, with its mysteriously just right dark energy, could be the rare jackpot winner where life somehow emerged. This isn't science fiction, it's the multiverse hypothesis, and it might explain why dark energy's strength seems so improbably fine-tuned. The math is startling. If dark energy were slightly stronger, galaxies would have ripped apart before life could evolve. Slightly weaker, and gravity would have crushed the universe back into oblivion. The fact that we exist in this razor-thin sweet spot feels like cosmic luck unless our universe isn't special at all, just one of countless trials where the numbers happen to line up. Eternal inflation, a leading multiverse theory, suggests new universes constantly bubble into existence, each with random physical constants. Most are sterile, but a handful, by sheer statistics, land in the habitable zone. Here's where it gets wild. Those other universes might be nudging ours. If bubble universes collide, like soap foam merging, their gravitational imprints could subtly warp our expansion rate. Some researchers speculate that anomalies like the Hubble tension or uneven expansion could be echoes of these collisions, cosmic bruises from a neighboring universe we'll never see. Others propose that dark energy itself leaks between universes through hidden dimensions, a phantom force bleeding into our reality. But how do we test something this bizarre? One clue might lie in the cosmic microwave background. Strange cold spots or odd polarization patterns could be bruises from ancient collisions. Gravitational wave detectors might someday catch ripples from a multiversal encounter. Or perhaps the answer is darker. If the multiverse is real, we may never know for sure, trapped forever in our pocket of space, wondering what lies beyond the veil. The multiverse idea forces a humbling shift in perspective. Instead of asking why our universe expands the way it does, we might instead ask how often it happens this way in an infinite sea of possibilities. It's a radical twist on cosmology's grandest questions, one that turns our search for answers into a cosmic game of probability, where the only certainty is that reality is far stranger than we dreamed. Hold a ruler to the cosmos and you'd find something bizarre. The universe is almost perfectly flat. Not flat like a sheet of paper, flat in the cosmic sense, where parallel lines never meet. Angles in triangles add up to exactly 180 degrees, and space stretches without any overarching curvature. This isn't just a neat coincidence. That flatness is a smoking gun, pointing back to conditions in the universe's first moments, so finely tuned they border on the impossible. To understand why this is strange, picture a balloon inflating. If you start with even a tiny bump or dent, blowing it up smooths those imperfections, but it doesn't erase them entirely. Now imagine inflating that balloon to the size of the observable universe. Any initial curvature, no matter how slight, should still be detectable today. Yet when we measure the cosmos with instruments like the Planck satellite, the curvature is so negligible it might as well be zero. The universe didn't just end up roughly flat, it's flat to 1 part in 10,000, like rolling a die and landing on the same number 10,000 times in a row. This precision defies random chance. In the standard Big Bang model without inflation, the universe's curvature should have grown more pronounced over time. Too much matter and space would curve inward like a sphere, eventually collapsing in a big crunch. Too little, and it would curve outward like a saddle, stretching into infinite thinness. Instead, we're perched on a razor's edge between these extremes, with a density almost exactly at the critical balance point. How inflation, that explosive hyper-expansion in the universe's first fraction of a second, offers a compelling answer. By stretching space so violently, it could have smoothed out any primordial curvature, ironing the cosmos flat like a cosmic steamroller. But here's the catch: inflation doesn't just predict flatness, it demands it. The theory only works if the inflattened field, the hypothetical engine behind the rapid expansion, had just the right properties to stretch space by the correct astronomical factor. A little too weak and curvature would remain. A little too strong and space would tear apart entirely. This fine-tuning is so exact it sparked heated debate. Is inflation a flawless solution, or does it merely replace one mystery with another? Some theorists argue this isn't a problem at all, that the inflattened field naturally settles into the required state through quantum processes. Others see it as a clue pointing to deeper physics, like a multiverse where countless universes with different curvatures exist, and we just happen to inhabit the flat one. The wildest possibility, that flatness isn't fundamental, but an illusion, a local artifact of our observable universe, while the greater cosmos beyond our horizon bends in ways we'll never see. The stakes are cosmic. If the universe isn't perfectly flat, it could mean inflation isn't the full story, or that dark energy's grip on expansion will change over time, warping space in unexpected ways. For now, the Planck data's razor-thin margin of error leaves room for doubt, like a carpenter's level bubble not quite centered. Future experiments like next-generation cosmic microwave background telescopes aim to shrink that uncertainty further. But until then, the universe's flatness remains both a triumph of theory and a whisper of something deeper lurking beneath the numbers. Dark energy may be the leading explanation for cosmic acceleration, but it's not the only game in town. Some scientists argue we're chasing a phantom, that rather than invoking an invisible force, we should reconsider how gravity itself behaves on the grandest scales. This bold alternative comes in two flavors: modified gravity theories that tweak Einstein's equations, and emergent gravity approaches that rewrite the rules entirely. Each challenges dark energy's dominance while raising their own tantalizing questions. Take modified Newtonian dynamics, or MND, an idea originally proposed to explain galaxy rotations without dark matter. When astronomers noticed stars orbiting galaxies faster than Newton's laws predicted, MND suggested gravity might strengthen slightly at extremely low accelerations. Now some researchers are asking, could a cosmic-scale version explain acceleration without dark energy? Theories like relativistic MND or tensor vector scalar gravity attempt this, proposing that spacetime responds differently in the near vacuum between galaxies. The appeal is obvious. No mysterious dark energy needed, just adjusted gravity. But there's a catch. These models struggle to match all the data, like the precise patterns in the cosmic microwave background or the way galaxy clusters bend light. Worse, they often require their own hidden components, trading dark energy for equally puzzling fields. Then there's emergent gravity, a radical rethink from the ground up. In this view, gravity isn't a fundamental force, it's a side effect of quantum entanglement, like how temperature emerges from countless atoms jiggling. Dutch physicist Erik Verland's version suggests cosmic acceleration arises because dark energy is actually dark information, a kind of quantum memory etched into spacetime itself. Imagine the universe as a hologram where gravity is just pixels reorganizing on some grand cosmic screen. It's a beautiful idea, but verification is brutally hard. Current tests like galaxy motions in sparse regions show hints but no smoking gun. Why does dark energy still win? One word: versatility. However strange dark energy seems, it fits an astonishing range of observations, from supernova brightness to baryon acoustic oscillations, with a single adjustable parameter. Modified gravity often needs patchwork fixes for each new dataset. That said, dark energy's greatest weakness is also its strength. It's flexible enough to fit almost anything, making it hard to disprove. Until someone finds definitive evidence, perhaps imprints of modified gravity in gravitational waves, or a mismatch in how voids expand, the debate will rage on. What's fascinating isn't just the competing ideas, but what they reveal about science itself. When faced with cosmic mysteries, we don't just gather data, we reinvent physics. Whether dark energy holds or falls, the real discovery may be how little we truly grasp about the fabric of reality. Right now, the cosmic microwave background surrounds us like a whisper from the dawn of time, a faint glow of microwave radiation left over from the Big Bang. But as the universe races outward, this ancient light is being stretched thinner and thinner, its photons pulled to longer, weaker wavelengths by the relentless expansion of space. One day, far in the future, it will vanish entirely, leaving no trace for astronomers to detect. So what happens when the last echo of creation fades into silence? And how will future civilizations unravel the universe's origins without it? Imagine standing in a vast, darkening hall where the last embers of a fire are slowly cooling. That's our universe in a trillion years. The CMB's once brilliant afterglow stretched into radio waves so long and feeble they slip through our detectors unnoticed. By then, every galaxy outside our local group will have fled beyond the cosmic horizon. their light stretched past infrared into utter invisibility. The CMB, which today gives us baby pictures of the cosmos just 380,000 years after the Big Bang, will be redshifted to wavelengths longer than the observable universe itself. The universe's birth certificate, in effect, will have disintegrated. This raises a chilling question: how will future scientists even know the Big Bang happened? Without the CMB's telltale patterns, the tiny temperature fluctuations that seeded galaxies, they might see only an unchanging island universe drifting in eternal darkness. Some researchers speculate they'd have to rely on fossil clues, like the ratios of ancient elements forged in the first few minutes after the Big Bang. Hydrogen, helium, and traces of lithium could hint at a fiery beginning, but these fingerprints are far less detailed than the CMB's rich tapestry. Others suggest turning to galactic archaeology. The oldest stars in our galaxy's halo, relics from near the dawn of time, preserve chemical signatures of the first stellar generations. By studying them, future astronomers might reverse engineer the universe's youth, though it'd be like reconstructing a symphony from a single lingering note. The wild card: gravitational waves, primordial ripples from inflation, if ever detected, could persist as a cosmic background hum long after the CMB fades, offering a new window into the universe's first moments. But here's the twist: this slow erasure of the past isn't just a distant thought experiment. It's already happening. Every second, the CMB grows slightly dimmer, its photons stretched further toward oblivion. In a sense, we're living in a privileged sliver of time, late enough to see galaxies and cosmic structure, but early enough to still catch the echo of creation itself. Future civilizations might never know the universe had a beginning at all, let alone one as violent and magnificent as ours, and that makes today's golden age of cosmology feel even more precious, a fleeting chance to read the universe's story before the pages turn to dust. Black holes, those cosmic vacuum cleaners that devour everything in their path, might be doing more than just consuming matter. Some scientists speculate they could be secretly shaping the universe's expansion itself. Think of them not as endpoints, but as engines warping spacetime in ways we're only beginning to grasp. One provocative idea suggests that supermassive black holes lurking at the centers of galaxies might be entangled with dark energy's mysterious influence. Could these gravitational monsters be tugging at the fabric of the cosmos, accelerating its expansion like invisible hands stretching rubber? The black hole universe hypothesis takes this even further. Imagine if every black hole isn't just a collapsed star, but a wormhole to another universe, or even the seed of an entirely new cosmos. In this wild scenario, our universe could be nested inside a black hole from a parent universe, with each black hole we see birthing its own cosmic realm. It's a dizzying thought, but here's the kicker. If black holes store information in their event horizons, as quantum physics suggests, that data could influence spacetime's behavior on a universal scale. Some theorists propose that the energy tied up in these cosmic vaults might mimic dark energy, creating the illusion of expansion when it's actually black holes altering the rules of gravity itself. Observational clues add fuel to the fire. Recent studies found that supermassive black holes appear to grow faster than expected, as if feeding on something beyond ordinary matter. Could they be siphoning energy from the quantum vacuum or even from other dimensions? Others point to odd correlations between black hole activity and the large-scale structure of the universe, like eerie synchronizations between galaxy clusters and the voids around them. Of course, these ideas are fringe for now. Mainstream cosmology still sees black holes as local phenomena, not cosmic architects, but with mysteries like dark energy and the Hubble tension-defying explanation, scientists are digging deeper into the possibility that the universe's biggest enigmas might be hiding in its darkest corners. After all, if black holes can bend light and twist time, who's to say they aren't bending the fate of everything else along with them? Time might feel constant to us, ticking forward second by second without fail, But what if the universe's runaway expansion is secretly stretching time itself? Imagine a cosmic hourglass where the sand flows slower the more space expands, making the distant future appear frozen from our vantage point. This isn't just poetic speculation. Some theories suggest that as galaxies accelerate away, the very fabric of time could warp in ways that defy our everyday experience. Einstein's relativity already tells us time isn't absolute. Clocks tick slower near massive objects like black holes or when moving at high speeds, but cosmic expansion adds a bizarre twist. If space stretches fast enough, light from distant galaxies gets redshifted into oblivion. Their signals stretched so thin they eventually vanish. But what happens to time in those far-off regions? Some models propose that as expansion accelerates, time dilation could become extreme. From our perspective, events in those distant galaxies might appear to slow to a crawl, like a video buffering endlessly. The end of star formation, the death of the last suns, all of it could seem suspended in a ghostly slow motion, even as time passes normally for observers trapped there. This idea ties into the concept of the cosmic event horizon. Just as a black hole's event horizon marks a point of no return for light, the universe's expansion creates horizons beyond which we'll never see future events. As galaxies cross this boundary, their clocks would from our view grind infinitely slowly, their final moments stretched across eternity. It's as if the universe is writing its own history, but the last chapters are being smeared into illegibility by expansion. But here's where it gets stranger. If time's flow is tied to gravity and motion, could dark energy's grip on spacetime also alter it? One controversial theory suggests that in a universe dominated by dark energy, time itself might eventually lose its direction on cosmological scales. Entropy, the arrow of time, could become so diluted that causation blurs past and future, mingling in ways we can't comprehend. Of course, we won't live to see these effects. They'd unfold over trillions of years, long after Earth is gone. Yet the mere possibility forces us to confront how little we understand about time's true nature. Is it a river, a fabric, or something far more malleable shaped by the universe's expansion like putty in an invisible hand? The answer might rewrite not just cosmology, but our place in the story of time itself. At first glance, the universe's rapid expansion should have made it impossible for galaxies and galaxy clusters to form at all. Think of it like trying to build a sandcastle as the tide rushes in. Every time you pack a handful of sand, the waves tear it apart. So how did cosmic structures manage to grow against the relentless pull of expanding space? The answer lies in an epic tug of war between two invisible forces, dark energy pushing everything apart and dark matter pulling it all together. Dark matter is the unsung hero of this story. Unlike ordinary matter, it doesn't interact with light or radiation. It only feels gravity's grip. In the early universe, while expansion was stretching spacetime, dark matter's gravitational pull created dense regions where gas could pool, like invisible scaffolding for galaxies to form. These dark matter halos acted as cosmic glue, counteracting expansion's dispersing effect just enough for ordinary matter, hydrogen, helium, to clump together and ignite the first stars. Without dark matter's anchoring gravity, the universe would be a vast, empty void, its matter too diluted to ever coalesce. But here's the puzzle. Simulations of this process, like the famous Millennium Run, show dark matter forming structures too efficiently. They predict more galaxy clusters and thicker cosmic filaments than we actually observe. Some galaxies in the early universe, like the unexpectedly massive Sparkler galaxy spotted by the James Webb Space Telescope, appear to have formed far sooner than models allow. It's as if something, perhaps an unknown property of dark matter or an overlooked feedback effect from early stars, was subtly slowing structure formation in ways we don't yet understand. One tantalizing clue comes from the cosmic microwave background. Its faint temperature fluctuations, imprinted when the universe was just 380,000 years old, already show the seeds of future galaxies, slightly denser patches where dark matter's gravity had begun working against expansion's tide. Over billions of years, those tiny overdensities snowballed into the galaxies we see today. Yet the exact recipe, how much dark matter was needed, how quickly it clustered, and how ordinary matter followed, remains incomplete. Could there be more to the story? Some theorists propose that dark matter isn't entirely dark. A small fraction might interact weakly with light or itself, creating friction that delayed structure formation just enough to match observations. Others suggest primordial magnetic fields or cosmic strings, defects in spacetime left over from the Big Bang, could have altered the playing field. The wildest idea: that dark energy wasn't always constant. If it briefly weakened during the universe's adolescence, it might have given dark matter a critical window to build galaxies unhindered. What's clear is that structure formation isn't just a historical footnote, it's an ongoing experiment. Right now, as you watch this, dark matter halos are still growing, galaxies are still merging, and expansion is still stretching the cosmic web. The balance between these forces shapes everything we see, from the smallest dwarf galaxy to the largest superclusters. And until we solve the mystery of how they danced together in the early universe, we're missing a crucial chapter in the story of how everything came to be. Measuring the universe's expansion seems straightforward. Point a telescope, collect data, crunch the numbers. But what if the tools we're using have hidden biases, like a slightly warped ruler throwing off every measurement? The reality is, even our most trusted cosmic yardsticks, Type Ia supernova and baryon acoustic oscillations, may carry subtle imperfections that skew our view of how fast space is stretching. Take Type Ia supernova, those brilliant standard candles that revealed dark energy in the first place. The assumption has always been that these stellar explosions shine with consistent brightness, allowing us to gauge their distance precisely. But recent studies suggest they might not be as uniform as we thought. Different stellar environments, like the metallicity of a host galaxy or the way white dwarfs accumulate matter before detonating, could introduce tiny variations in peak brightness. It's like assuming every light bulb in a city is identical, only to realize some are dimmer or brighter based on the factory that made them. Even a 5% discrepancy could tilt the Hubble Constant's value significantly, potentially inflating the tension between measurement methods. Then there's cosmic dust, the silent saboteur. Drifting between galaxies, these microscopic particles can absorb and scatter light, making distant supernovae appear dimmer than they truly are. If dust clouds are thicker in certain regions of space, our calculations could mistake their dimming effect for a faster expansion rate. Teams have tried correcting for this by analyzing how dust reddens light, but unknowns remain, like whether dust properties change over cosmic time or vary across different galactic environments. Baryon acoustic oscillations, BAO, the cosmic ruler etched into the clustering of galaxies, face their own challenges. These ripples from the early universe should serve as perfectly spaced markers, but galaxy surveys might be missing subtle distortions. For instance, if galaxies form more efficiently in dense regions, their distribution could appear slightly compressed, mimicking a slower expansion. Alternatively, peculiar velocities, galaxies being tugged by local gravity rather than cosmic expansion, could smear the BAO signal like a smudged fingerprint. The good news: scientists aren't taking these uncertainties lightly. Next-generation projects like the Vera Rubin Observatory and the Dark Energy Spectroscopic Instrument are cross-checking supernova and BAOs with unprecedented precision. Some teams are even turning to entirely independent methods, like gravitational lensing or time delays in quasars, to triangulate the truth. The goal isn't just to resolve biases, it's to ask whether the Hubble tension is a clue to new physics or simply a cosmic mirage created by our imperfect tools. Until we know for sure, every measurement remains an open question. Neutrinos are the ghosts of the particle world, zipping through matter almost undisturbed. so light they barely tip the scales, yet so abundant they outnumber atoms 1,000,000,000 to 1. These cosmic phantoms might seem too wispy to impact something as colossal as universal expansion, but their collective whisper could be subtly shaping spacetime itself. For decades, we thought neutrinos were massless, racing through the cosmos at light speed. Then came the bombshell: they have mass, just a fraction of an electron's, but enough to add up across the trillions passing through your body every second. That faint heft means they feel gravity's pull, potentially slowing expansion like a cosmic drag. Yet here's the twist: as the universe stretches, neutrinos lose energy, cooling until they move sluggishly compared to light. Some theories suggest this shift might let them mimic dark energy's effects, not by pushing space apart, but by altering how gravity behaves on vast scales. One radical idea, dubbed neutrino dark energy, proposes these particles interact with a mysterious quantum field that grows stronger as space expands. Imagine a seesaw. As neutrinos lose momentum, this hidden field gains strength, accelerating expansion in their place. Another wild possibility: neutrinos might decay into even stranger particles over eons, releasing energy that fuels cosmic stretching. Then there's the neutrino floor, the point where expansion redshifts their energy so much they become nearly frozen, like fireflies trapped in amber. In this state, they could form a diffuse cosmic fog, subtly warping spacetime's geometry. We're already hunting for clues. Experiments like Katrin aim to pin down neutrino mass with unprecedented precision, while telescopes track how galaxy clustering shifts in neutrino-rich models. What's haunting is how much we don't know. Neutrinos could be passive bystanders or silent architects, their fingerprints hidden in the universe's accelerating heartbeat. Either way, their story reminds us even the faintest particles can sway the fate of everything. What if our universe isn't the first or the last in an endless cycle of cosmic rebirth? Picture a cosmic pendulum swinging between expansion and collapse, where every big bang is followed by a big crunch, only to explode outward again in an infinite loop. This is the tantalizing premise of cyclic cosmology, a radical alternative to the one and done universe we usually imagine. Instead of fading into cold emptiness or tearing apart in a big rip, the cosmos might be locked in an eternal dance, collapsing and expanding like a lung breathing in and out. One of the boldest versions comes from physicist Roger Penrose, who proposed conformal cyclic cosmology, a model where the far future of one universe becomes the Big Bang of the next. As space stretches to near infinity, particles lose their mass, distances become meaningless, and the universe resets to a state identical to the primordial singularity. It's like heating a steel bar until it glows white hot. At a certain point, it loses all memory of its original shape, ready to be forged anew. Penrose even claims to have found evidence in the cosmic microwave background, concentric rings of temperature variations that might be gravitational echoes of collisions between black holes from a previous cosmic cycle. But cyclic models face formidable hurdles. The biggest, entropy. The second law of thermodynamics states that disorder always increases, meaning each new cycle should start with more chaos than the last. Over infinite cycles, the universe should have long ago descended into maximum entropy, a featureless soup of particles. Yet here we are in a universe with galaxies, stars, and planets. Some theorists propose workarounds like phantom energy, a form of dark energy that grows so powerful it resets entropy by tearing space-time apart at the quantum level before the next cycle begins. Others suggest gravity itself could reverse entropy's arrow during collapse, though no known physics supports this. Then there's the crunch itself. For the universe to rebound, gravity would need to overcome dark energy's relentless push, something only possible if dark energy weakens over time or if exotic matter with negative energy emerges. Observations so far favor dark energy's staying power, making a big crunch seem unlikely. Yet some cyclic models dodge this entirely, suggesting universes bounce at a microscopic scale, never fully collapsing. The most haunting implication: if the universe is cyclic, everything we see, every galaxy, every law of physics, might just be one variation in an infinite series. The constants we take as fixed, like the strength of gravity or the mass of an electron, could shuffle with each cycle, creating universes wildly different from our own. It's a dizzying thought. We might be living in the one cycle where, by sheer chance, the numbers lined up just right for life to emerge. For now, cyclic cosmology remains a beautiful, if unproven, idea. But it offers something profound, a vision of the cosmos where endings are also beginnings, and where the universe, against all odds, might never truly die. What if the act of observing the universe doesn't just record its behavior but shapes it? It's a dizzying idea straight out of quantum mechanics, where particles seem to choose their state only when measured. Now, some theorists are asking, could consciousness itself on a cosmic scale influence how the universe expands? This isn't just philosophical musing. It's a fringe but fiercely debated hypothesis that blurs the line between mind and cosmos. Start with the quantum enigma. In the famous double-slit experiment, particles behave as waves when unobserved, but collapse into definite positions the moment they're measured. This observer effect suggests that at the quantum level, reality might be participatory, shaped by the act of observation. But does this principle scale up? Could the collective observation of galaxies, black holes, or even conscious beings like us subtly nudge the universe's expansion parameters? Some interpretations of quantum mechanics, like the von Neumann-Wigner hypothesis, flirt with this possibility, suggesting consciousness causes the collapse of quantum probabilities into concrete reality. Extend this idea to cosmology, and you get wild scenarios. Perhaps the universe's acceleration isn't driven by dark energy alone, but by some vast, interwoven network of observation, like a cosmic feedback loop where space-time decides how to stretch based on what's looking at it. Critics dismiss this as metaphysical speculation, and for good reason. There's zero empirical evidence linking consciousness to gravity or space-time curvature. The sheer scale difference between quantum weirdness and cosmic expansion seems insurmountable. Yet intriguingly, some models in quantum gravity suggest that information, the raw material of observation, might be fundamentally tied to space-time structure. In holographic principle theories, for instance, the universe could be a projection of data encoded on its boundaries, where every observation updates the cosmic code. The most radical version, that consciousness isn't just affecting the universe, it is the universe. Philosophers like Bernardo Kastrup argue that reality might be a kind of mind at large, with cosmic expansion reflecting its evolving thought. Even physicists like Sir Roger Penrose hint at connections between quantum processes in brain microtubules and the fabric of spacetime, though these ideas remain controversial. Of course, mainstream cosmology shrugs this off. Dark energy's effects are measurable across billions of light-years, far beyond any plausible influence from earthbound minds. But the question lingers: if observation shapes reality at the smallest scales, why couldn't it, in some unfathomable way, ripple upward? Maybe we're not just passive witnesses to the universe's expansion, but silent participants in its unfolding story. Dark energy and dark matter sound like cosmic opposites. One flings galaxies apart while the other binds them together, yet they share an eerie symmetry. Together, they make up 95% of the universe's total content, while everything we can see, stars, planets, you and me, is just cosmic dust in comparison. But what if their opposing roles aren't a coincidence? What if they're two sides of the same shadowy coin? Start with dark matter, the universe's invisible scaffolding. Unlike ordinary matter, it doesn't emit, absorb, or reflect light, but its gravity tugs on everything. Imagine a cosmic spiderweb, its strands woven so finely they're undetectable, yet strong enough to shape galaxies and clusters. Without dark matter's pull, galaxies would spin apart like shattered wheels, their stars flung into the void. Now contrast that with dark energy, the phantom force stretching space itself. Where dark matter clumps and anchors, dark energy smooths and disperses, its repulsive push overwhelming gravity on cosmic scales. It's as if the universe has two silent hands, one squeezing matter together, the other prizing it apart. But here's where it gets strange. These forces aren't just balanced, they're eerily matched in magnitude. Today, dark energy dominates, driving accelerated expansion. Yet in the early universe, dark matter's gravity held sway, allowing structures to form. The timing feels suspiciously precise, as if some deeper mechanism tuned their rivalry to allow galaxies, stars, and ultimately life to exist. Some theorists wonder, could dark energy and dark matter be different phases of a single, unified dark sector? One provocative idea suggests dark matter particles might decay into dark energy over time, slowly converting the universe's glue into its solvent. Others propose they interact through an unknown fifth force, a hidden dialogue woven into the fabric of space-time. There's even a wild-card theory that dark matter's gravity could screen dark energy in dense regions, explaining why galaxy clusters seem to resist expansion more than expected. Yet every attempt to link them runs into obstacles. Dark matter behaves like a particle, clumping under gravity, while dark energy acts like a property of space itself, smooth and unyielding. Experiments hunting dark matter, like underground detectors or particle colliders, have come up empty, while dark energy's effects are only visible across billions of light years. If they're connected, the bridge between them remains hidden in the equations. What's undeniable is their partnership in shaping cosmic destiny. Dark matter builds the stage, dark energy decides how long the play runs. And until we understand their relationship, we're stuck with a universe that's 95% unknown, a reminder that the darkest corners of reality might hold the brightest secrets. Billions of years from now, the night sky will tell a different story, one of vanishing stars and growing darkness. As cosmic expansion accelerates, distant galaxies will first redshift into invisibility, their light stretched beyond detection. Then closer galaxies will follow, leaving island universes isolated in an ever-growing void. But the real terror comes when expansion turns inward, severing the gravitational bonds that hold our own galaxy together. Stars will drift apart like ships, losing sight of one another in an endless ocean, until each solar system becomes its own lonely island in the cold. For any civilization surviving into this epoch, the challenges would be existential. The first casualty, energy. As galaxies disperse, the raw materials for star formation, hydrogen clouds, stellar debris, will become too scattered to coalesce. No new stars means no new energy sources, forcing civilizations to ration dwindling stellar remnants or tap into black hole thermodynamics for survival. Some might attempt megastructures to capture every photon from decaying white dwarfs, while others could resort to stellar husbandry, deliberately slowing fusion in remaining stars to extend their lifespans. Yet even these desperate measures have an expiration date. Then comes the information crisis. With all galaxies beyond the local group receding faster than light, the cosmos will lose its history. Future astronomers would peer into the sky and see only darkness with no cosmic microwave background. No redshift patterns, no evidence the universe ever had a beginning. Any records of the Big Bang or early cosmic eras would survive only in fragile local archives, vulnerable to entropy's relentless decay. Civilizations might harbor myths of a greater cosmos beyond their prison walls, but proving it would be impossible. Could life adapt? Some theorists speculate about post-biological intelligence's consciousness encoded in superconducting circuits or plasma clouds near dying stars, operating at near absolute zero temperatures to minimize energy use. Others imagine civilizations entering eternal hibernation, waking only in fleeting cycles to conserve resources, the most radical possibility, engineering an escape. If higher dimensions or quantum tunneling could breach the cosmic horizon, some might attempt exodus to younger universes, though this ventures into pure speculation. Yet the cruelest irony is this: the universe's expansion isn't just stealing light and heat, it's erasing possibility itself. In time, no new structures can form, no new energy gradients arise. The universe becomes a graveyard of frozen embers, where even the most resilient life must eventually succumb to the cold, unless, of course, they rewrite the rules first. The universe is supposed to be isotropic, the same in all directions, but what if it's subtly lopsided? Hidden in the cosmic microwave background, that ancient afterglow of the Big Bang, lies a bizarre pattern cosmologists call the axis of evil. This ominous-sounding feature isn't some cosmic conspiracy. It's a strange alignment of temperature fluctuations that shouldn't exist if the universe expanded uniformly. Instead of random hot and cold spots scattered evenly, these fluctuations seem to line up along a particular plane, almost as if the early universe had a preferred direction. It's like rolling a die 1,000 times and getting sixes clustered along one invisible line. Statistically, it shouldn't happen. Equally puzzling are the galaxy clusters that refuse to follow the script. Some appear to be streaming at dizzying speeds toward unseen structures beyond our observable horizon, as if tugged by cosmic currents we can't map. Others show peculiar rotational alignments across vast distances, spinning in eerie synchrony like dancers choreographed by invisible hands. The most famous of these, the dark flow, involves thousands of galaxies hurtling toward a single patch of sky at speeds exceeding 600 kilometers per second, far faster than standard expansion models allow. Could these be flukes or signs of something deeper? Then there's the Hubble tension itself, the stubborn mismatch between how fast we measure the universe expanding today versus predictions based on its infancy. The numbers disagree by enough to rule out random error, suggesting either systematic biases in our measurements or a fundamental gap in our understanding of cosmic evolution. Some speculate these anomalies might trace back to primordial irregularities, wrinkles in space-time left over from inflation that never fully smoothed out. Others wonder if dark energy isn't uniform but lumpy, warping expansion rates in unexpected ways. The wildest theories go further. Could these oddities be fingerprints of a pre-Big Bang universe, imprints from collisions with other cosmic bubbles in a multiverse, or evidence that gravity itself behaves differently on scales larger than we've tested? Mainstream cosmology treats these anomalies with caution, but their persistence gnaws at the edges of our models. Every unexplained asymmetry is a whisper that the universe might be stranger and far less random than we've dared to imagine. The question isn't just whether these cracks in our theories are real. It's what they're trying to tell us about the fabric of reality itself. Human history is full of mysteries we once thought unsolvable: why the stars moved, what caused disease, how lightning worked. Each time we push the boundaries of understanding, turning the unknown into the known. But when it comes to the universe's accelerating expansion, we might be facing something different. A puzzle where the answers could lie forever beyond our reach, not for lack of trying, but because the cosmos itself is erasing the clues. Consider the sheer scale of the challenge. Dark energy's effects are written across billions of light years, but its nature is hidden in the quantum realm, a realm where our two most powerful theories, general relativity and quantum mechanics, refuse to speak the same language. To crack this, we'd need to observe the universe with impossible precision, across impossible distances, for impossible spans of time, and yet we're not surrendering. A new generation of telescopes is gearing up to hunt for dark energy's fingerprints. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will map billions of galaxies to trace how cosmic structures grow under dark energy's push. Euclid, Europe's dark energy hunter, will measure the shapes and positions of galaxies with microscopic accuracy, searching for distortions that betray dark energy's grip on spacetime. But what if these missions deepen the mystery instead of solving it? The history of cosmology is littered with surprises. Every time we build a better instrument, we uncover phenomena no one predicted. The James Webb Space Telescope, for instance, recently spotted galaxies in the early universe so massive they shouldn't exist under current models. Could dark energy be another cosmic curveball, a sign that our theories are just approximations of a far weirder reality? Some theorists fear we're like ants trying to deduce the rules of chess by watching a single move, missing the full game unfolding around us. Even if we never fully solve these riddles, the pursuit itself changes us. Every failed experiment, every stubborn anomaly, forces us to rethink the fundamentals of reality. Maybe dark energy isn't a thing to discover but a mirror showing the limits of our current physics, a cosmic invitation to rewrite the rules. Or perhaps, in some distant future, humanity will unlock technologies that let us probe dimensions or energies we can't yet imagine, turning today's mysteries into tomorrow's textbooks. For now, the universe keeps its secrets close, stretching them farther away with each passing second. But whether we find answers or only deeper questions, the journey peering into the abyss and daring to ask is what makes us cosmic storytellers in the grandest tale of all. From the phantom grip of dark energy to the eerie uniformity of the cosmic microwave background, these 25 unsolved questions aren't just gaps in our knowledge, they're portals to deeper mysteries. Each one peels back another layer of the universe's grand illusion, revealing how much we still don't understand. Why does dark energy's strength defy quantum predictions? How do galaxies form faster than our models allow? And what, or who might be watching from beyond the unobservable universe? These aren't just scientific puzzles, they're cosmic invitations daring us to rethink reality itself. Consider the Hubble tension, a numbers game so precise it hints at undiscovered physics. Or black holes, those gravitational enigmas that might hold keys to dark energy's origins. Even time itself, once thought immutable, could be stretching thin as the universe accelerates toward an uncertain fate. And let's not forget the elephant in the room, the vacuum catastrophe, where our best theories overshoot reality by a factor of 1 followed by 120 zeros. That's not a rounding error, it's a scream from the universe that we're missing something fundamental. Yet here's the beautiful part, every unanswered question is a frontier waiting to be crossed. Maybe the solution lies in a lab experiment yet to be designed, or in data pouring from a telescope not yet built. Or perhaps the key is hiding in plain sight, overlooked because it didn't fit the old paradigms. One thing's certain, the universe isn't done surprising us, so stay curious, keep looking up. Who knows, maybe the person who cracks one of these cosmic riddles is watching this right now. And if that's you, don't keep it to yourself. Drop a comment below and tell us which mystery fascinates you most. Is it the fate of the universe, the true nature of dark matter? Or something even wilder we haven't yet imagined? Hit like if you're as obsessed with these questions as we are, and subscribe to join us as we chase the next big revelation. The universe is full of stories, let's uncover them together.